In this session, I'd like to continue the discussion of joint distributions for random variables. And we're going to discuss joint cumulative distributions and statistical independence. So recall that previously we had discussed that if we had random variables x and y, they can have probability mass function or probability density functions, small f sub x and small f sub y. They have cumulative distributions, capital F sub x, capital F sub y, and the minimum that we want to be able to calculate are the expectation of x and the variance of x, and the standard deviation of x, and the expectation of y, the variance of y, and so the standard deviation of y. Now, if we have cumulative distributions, f sub x and f sub y, can we get a joint cumulative distribution? So we have cumulative distribution capital F sub x for x, and a cumulative distribution capital F sub y for y. Can we define a cumulative distribution, a joint cumulative distribution, f sub x, y? Okay. All right, well, let's split this. We'll consider two cases. One will be the case where both capital X, both the random variables x and y are discrete random variables. And it's possible to calculate their individual PMFs, small f sub x and small f sub y, and their individual CDFs, capital F sub x and capital F sub y. We will then calculate a joint cumulative distribution for x and y. Okay, what was the meaning of capital? Recall the meaning of capital F sub x of a. That means that's the value, which is the probability that the random variable x takes a value less than or equal to a, and that can be calculated by the summation for all values, allowed values of x less than or equal to a, of the PMF evaluated at x. And similarly, the notation capital F sub y of b, that means the probability that y is less than or equal to b. That's the summation over all the allowed values of y, which are less than or equal to b, of the PMF for y evaluated at y. Okay. So then the recall that the joint PMF f sub xy was defined to be the probability that x is equal to x and y takes the value y. So then we define the joint cumulative distribution as the probability f sub xy of ab is a probability that x is less than or equal to a, and at the same time that y is less than or equal to b. That's the summation over all x is less than or equal to a, so all y is less than or equal to b, such that the PMF f sub xy, the summation of the PMF f sub xy evaluated at x and y. Okay, so it's defined analogously. So let's do an example. A fair coin is tossed twice. X is the number of heads, y is the number of tails. So if we're going to find a joint cumulative distribution, one way to do it would be to find the joint PMF first. Okay. So what is the joint PMF as an exercise? We could do this, and there are 4 equally likely outcomes. So here x is 2 and y is 0. Here x is 1 and y is 1. Here x is 1 and y is 1. And here x is 0 and y is 2 from the definitions of x and y. X is the number of heads, y is the number of tails. Okay. So the probability that, and each of these outcomes is equally likely. So the probability of each one of these outcomes in the sample space is 1 over 4. So then we can get the values for the joint PMF. The probability, right? So f sub xy of 2, 0 is a quarter. F sub xy of 1, 1 is a quarter plus a quarter, 2 quarters. F sub xy of 0, 2 means 2 heads is, and no, sorry, means 2 tails and no heads. That's equal to 1 quarter. So now we can give the joint PMF this way. F sub xy of xy equals 1 quarter, x equals 2, y equals 0. 1 half, x equals 1, y equals 1. 1 quarter for x equals 0, y is equal to 2, and 0 for anything else. Now, having found the PMF, we can now find the joint CDF. So now, in the case of 2 continuous random variables, which have a joint PDF f sub xy, and they have marginal PDFs f sub x and f sub y, then the joint CDF is defined this way. F sub xy of AB is defined to be the probability that x is less than or equal to y and y is less than or equal to b. So that's the integral from minus infinity to x takes values from minus infinity to a, and y takes values from minus infinity to b, and you integrate the PDF over that region, which is an infinite rectangle. Okay, so remember that when you had continuous random variables x and y, and if they had PDFs f sub x and f sub y, if you were given the cumulative distribution, capital F sub x, you could find the PDF from the CDF by differentiating the CDF. Okay. So similarly, if I want to find if I have the cumulative distribution, the joint cumulative distribution, capital F sub xy, and I want to find the joint PDF, small f sub xy, then I take the partial derivative with respect to x and with respect to y, and that will get of the CDF, and that will give me the PDF. Okay, so let's do an example. I have CDF for random variables x and y defined by the CDF takes the value 1 minus e to the minus x times 1 minus e to the minus y for y, x and y both greater than 0, and it's 0 otherwise. Now, how do you find the PDF, small f sub xy? Well, you take the partial derivative with respect to x, and then you take the partial derivative with respect to y. So if I take the partial derivative with respect to x first, and for sensible PDFs and CDFs, it won't matter whether you take the partial with respect to x and then the partial with respect to y, or in the other way. So partial derivative with respect to x of the CDF That is, you take the derivative with respect to x, and you consider y just as if it was a constant. You don't differentiate anything with respect to y. All the derivatives are with respect to x. That will give you e to the minus x times 1 minus e to the minus y. Now you take the partial derivative with respect to y of this, treating x as if it was a constant, and you will get exponential minus x minus y. Remember, this is only for the region, this PDF, this CDF is only the case, this form of the CDF is only the case for x and y both greater than 0. Here, for the rest of the region, you would be differentiating 0, which would give you 0. Okay, so then the CDF, sorry, the PDF would be exponential minus x minus y for x greater than or equal to 0 and 0 otherwise. Okay. Marginal distributions. Okay, let's say I'm given a joint distribution and I want to get the distribution functions for the individual random variables. So I'm given a joint distribution for x and y, and I would like to get the distribution just for x, or the distribution function just for y. Okay, so that's the idea of a marginal distribution. So in the discrete case, you do it like this. Supposing that I have the joint PMF, small f sub x1, then I can find the PMF just for x by summing out the y. I take f sub xy, I take the joint distribution, I sum over all the allowed values of y, and then what I am left with when I do that is the PMF just for x. Okay, if I'm given the joint PMF for both x and y, and I only want the PMF for y, I can take the joint distribution for x and y, I can sum over all the allowed values of x, and then what I will be left with is the PMF just for y. Okay, in the continuous case, you don't do the summation, you do integration. So if I'm given the joint PDF f sub xy, and I just want the PDF for x, what I do is I integrate over all allowed values of y, and what I will be left with is f sub x. And similarly, if I take the joint PDF f sub xy, and I integrate out all the x's, I integrate over all the allowed values of x, from minus infinity to infinity, then I will only be left with f sub y of y. Okay. So those were how you calculate the marginal PMFs and PDFs given the joint PMFs and PDFs. Now, what if you have the cumulative functions? Then let's suppose you were given a joint CMF f sub xy from A to B. And what's f sub x of a? F sub x of a is the probability that x is less than or equal to a. And you can find that by taking f sub xy of ab, and then taking all the values, let b go to positive infinity. If you want f sub y of b, that's the probability that y is less than or equal to b. So take the joint CMF at ab, and let a go to infinity, and that you will be left with f sub y of b. Okay, similarly in the continuous case, if you're given the joint CDF f sub xy of ab, if you now let b go to positive infinity, that takes b out, the y part out, and all you're left with is f sub x of a. And similarly for f sub y of b, which is by definition, the probability that y is less than or equal to b, well, if you were already given f sub xy of ab, then you would let a go to positive infinity, and all you would be left with is f sub y of b. Okay, so let's do an example. Supposing that I'm given a joint PDF, f sub xy. As defined by f sub xy of xy equals x times 1 plus 3y squared over 4. And that's for x going between 0 and 2, and y going between 0 and 1, and 0 otherwise. Okay. Now I want to get out the marginal distributions. Let's see. If I want to get out the marginal distributions, then what would I have to do? I would have to integrate out the y in order to get f sub x, and I would have to integrate out the x to get f sub y of y. Or I can, another way to do it would be to find the joint CDF, f sub xy, restricted to the region where the joint PDF can be non-zero, and then I can take limits, and then I can differentiate. Okay. So f sub xy is the probability that x is less than or equal to x, and the random variable y takes a value less than or equal to y. That's given by integrating your PMF, right, from minus infinity to x and minus infinity to y. So x minus infinity to x and minus infinity to y. And in order to keep things correct and not to accidentally integrate out your x and your y, you should use dummy variables instead of x and y, use s and t. Okay, so you integrate out the PMF, sorry, the PDF, f sub xy of st from minus infinity to x and minus infinity to y, and that gives you the probability that x is less than or equal to x and y is less than or equal to y. Okay, then. Well, when you're integrating from minus infinity up to 0, you're getting zeros, and you're integrating from minus infinity up to 0, you're getting zeros, right? So in the where you get non-zero values, f sub xy, then it's the integral from 0 to x, 0 to y. And then what's this, right? S times 1 plus 3t squared over 4. S times 1 plus 3t squared over 4 ds dt. And if you do that integral, you get 1/8 y cubed plus y times x squared in the region where the joint PDF can be non-zero. Now, if you want the marginal CDFs, what do? If you've got the joint f sub x sub xy, and you just want f sub x, so you let y go to infinity. Okay. And in this case, remember, once you get past y is 1, everything drops off to 0, right? So you can just integrate up to, you can just take the limit up to 1, and you get 1/4 x squared. Right? And if you take y, if you have f sub xy, and you want to get f sub y from it, you take the limit as x goes to infinity of f sub x, y. But once you here, we go back to the definition. Once y gets bigger than 2, everything drops off. This thing here drops off to 0. So you only take it as far as the point where things would drop to 0. And that would x is equal to 2. So the limit as x goes to infinity becomes the limit as x goes to 2. 1/8 y cubed plus yx squared, which is 1/2 y cubed plus y. So you see, you've taken out the x, and all that's left is a function of y, which is the cumulative distribution for y, right? In the region where the PDF is non-zero. Okay. Now, if you want the PDFs from the CDFs, you take the derivatives of the CDF. So if you take the derivative of the capital F sub x, it gives me small f sub x. If I take the derivative of this 1/4 x squared, I get 1/2 x. And similarly for y, if I take the derivative of this cumulative distribution function for y, 1/2 y cubed plus y. Take the derivative with respect to y, I get 3/2 y squared plus 1/2. Okay. So that would be one way of finding the individual marginal PDFs. Now we come to the idea of statistical independence. Okay, so you recall independence of events. Events A and B are independent when probability of A intersection B is the probability of A times the probability of B. Recall that that also implies that the probability of A given B is the probability of A, and the probability of B given A is the probability of B when the individual probabilities are non-zero. Okay. Now, random variables. So that was independence of events. Now we're going to talk about the statistical independence of random variables. So random variables x and y are said to be statistically independent if and only if the joint distribution is the product of the individual distributions. So f sub x y, the joint PDF f sub x y of xy is equal to f sub x of x times f sub y of y, or the joint PMF f sub x y is equal to f sub the product of the individual PMFs f sub x times f sub y. Okay, so here's an example. X is a random variable with its PDF f sub x given by 0 for x less than 0, and it's 1 minus exponential minus x for x greater than or equal to 0. Okay. Let's suppose y is a random variable with PDF f sub y, defined by f sub y of y is 0 for y less than 0, and 1 minus exponential minus y for y greater than 0. And I will give you that x and y have a joint distribution function f sub xy, defined by f sub xy is equal to 0 for x less than 0 or y less than 0. And it's equal to 1 minus exponential of minus x minus exponential of minus y plus the exponential of minus x minus y for x greater than or equal to 0 and y greater than or equal to 0. So are x and y statistically independent? Well, what do we have to check? We have to check that f sub xy is equal to the product f sub x times f sub y. Is the joint PDF equal to the product of the individual PDFs? If it is, then we say that the two random variables are statistically independent. Okay, so this thing is defined in cases, right? In this region of the plane, it takes this form. In this region of the plane, it takes that form. So we consider the separate cases. So in case one, if x is less than 0, then the joint PDF is 0 and the individual PDFs are 0. So in that case, the joint PDF is the product of the individual PDFs. If x is less than 0, if y is less than 0, then the same thing happens. Now the remaining case, when x is non-negative and y is non-negative, then f sub xy, we take the form of f of xy, we do a bit of algebra, and we found that it is of the form product of f sub x of x times the product of f sub y of y. So in all of the cases, and for statistical independence, you would need for all of the cases, in all of the cases, the joint PDF is the product of the individual PDFs. And so the two random variables are statistically independent. Okay. So let me give you a problem. I have two black pens. Sorry, I have two blue pens, one black pen, one red pen. Two pens are selected at random without replacement. Let x be the number of blue pens selected. Let y be the number of black pens selected. I would like you to show that the random variables x and y are not statistically independent. Okay, so you should do that as a problem. Okay, supposing x and y are uniform on the region, right? Suppose that x and y are random variables and they're uniform random variables on the region 0 less than x less than y less than 1. What are the joint and marginal densities? Okay. Well, since they're uniform, it means that f sub xy takes a constant value and integrates to 1. So the way to do that on that region is to set f sub xy of xy equal to 2. How do I find the marginal density? Well, we can do the exercise. You find the marginal densities are f sub x of x equals 2 times 1 minus x, and f sub y of y is equal to 2y. And then you should show that if I take this product, f sub x is twice 1 minus x, and f sub y is equal to twice y. If I multiply it together, I'm not going to get 2, right? So they are not statistically independent. I should really say statistically independent and not independent. Okay. So that's it for this section.